So conformations. When you think of the word conform, if you lay down on a memory foam bed, we would say that the bed conforms to the shape of your body, right? So conforming has to do with the shape of something. So shapes we'll often refer to as conformations. And the shapes of the molecules affect their properties. We just saw that the rounder molecule had a lower boiling point than the straight molecule. Those are conformations. So if we talk about conformers, or they're sometimes called rotamers, which actually is easier to remember, this has to do with rotation. Conformers or rotamers are different shapes of the same molecule that are interconvertible by rotation around a single bond. So I have this model here. Sorry, YouTube people. But here's a model of ethane. There's a single bond between the carbon atoms, and that can rotate, and it does rotate. And so we can end up with different shapes based on how that rotation is, but they convert back and forth in between just by rotation around the bond. We don't have to break any bonds or do anything crazy. There's just this rotation. And so those are called conformers or rotamers. Those two words mean the same thing. These are examples of stereoisomers. We're going to be talking about a lot of different kinds of isomers, and so we're going to have to try to keep them straight. What's the difference between a music or perhaps a movie that's broadcast in stereo as opposed to one that isn't? Do you know? When you hear something in stereo, they recorded the music in a way that was sensitive to the shape. And so if the drummer's on the right and the bassist is on the left, then when you're listening to that from stereo speakers or stereo headphones, you hear the drum louder on the right speaker and the bassist louder on the left speaker. Okay? So it has to do with orientation in space. Stereoisomers. In a stereoisomer, the atoms are connected in the same way, but they're arranged different in space. They have different spatial arrangements. There are many types of stereoisomers. This is one kind, the rotamer or conformer, where we just have this rotation around a single bond. So when we have ethane, we have a carbon-carbon single bond, and we can get rotation around that bond, and we end up with two different shapes or conformations. One is called staggered and one is called eclipsed. And in these diagrams, what we're doing is we're looking from one carbon to the other carbon. So I'm looking so that the carbons overlap each other. That one's not plugged in very well. And so right now the one I'm holding up would be staggered. And if I rotate it a little bit, now they're eclipsed. Because what happens when we have a solar eclipse? The moon moves in front of the sun. They line up with where we are, and we can't see both of them. And so that's what is this eclipsed form. We're drawing them slightly off of each other so you can tell that they're still there. But when you're looking straight this way, the hydrogens line up with each other. And these hydrogens line up, and those hydrogens line up. And so everything lines up. That's eclipsed. And in between that, rotating part way, we get staggered, and now the hydrogens are staggered. So when we look down the center here, we see them staggered, they're spread out equally. Does that make sense? So we'll be using those terms, staggered and eclipsed. The bond between the two carbon atoms is a sigma bond. Remember, the sigma bond was symmetrical along the bond axis between those two carbons. So when you rotate it, the sigma bond is completely unaffected by rotation. So single bonds rotate. They do. The staggered conformation, this one is a little more stable than the eclipsed, just because these hydrogens, everybody wants their own space. That's how I think of it. All these atoms, they're like children in a family. They're like, get out of my space. Move over. Why are you sitting next to me? Stop looking at me. But they're they'd like to have a little more space. And so this way, the hydrogens on the adjacent carbons are a little closer together than in the staggered. In the staggered position, they have a little more space. If you have larger groups on there, it becomes more significant. So the staggered conformation is more stable, but we can't isolate the staggered conformation because it interconverts at room temperature so quickly for ethane. So these are different ways of drawing these ideas. So we're looking down the carbon-carbon bond. This is a dash wedge, three-dimensional attempt at drawing, right? Where here this hydrogen's coming out, that one's going back, and over here on the other carbon, it's the top hydrogen coming out and this one going back. This is more of a sawhorse picture. These are called Newman projections. And we use these a lot because they don't require as much drawing skill. So they're nice that way. So these are the different ways of drawing the staggered conformation. And this is the eclipsed. So looking down here, we see these hydrogens are lining up. So with the 3D dash wedge, we do it like this. The sawhorse, we'd see that both of these have one hydrogen sticking straight up. And this now looks more like a sawhorse. These are the legs. And in the Newman, we're going to see that they're overlapping each other. Okay, any questions? So draw the Newman projections for the staggered and eclipsed conformations of chloroethane. So there's a whole bunch of words you didn't know when you started the class. Newman projection, staggered, eclipsed. Oops, I changed the color there. I like the green. Eclipsed, conformations, and chloroethane. Lots of new words. Okay, first of all, what is chloroethane? Well, what's ethane? How many carbons? 2 carbons. So 2 carbons. And chloro then is a substituent. Which carbon is it on?
1.
It's on the 1 carbon, but it doesn't matter which one you put it on, because whichever one you put it on will be the 1 carbon. And then the rest of this is made up with hydrogens. So this carbon is going to have 3 hydrogens. This carbon is going to have 2 hydrogens. Sometimes we put the hydrogens before the carbon at the beginning. Sometimes we don't. So this carbon has 2 hydrogens and a chlorine attached to it. And this carbon has 3 hydrogens attached to it. So the Newman projection, we're going to take and draw a circle. I could cheat and use the circle thing, but I'm not going to. And so our carbon is right here in the middle, and then what we're drawing here are the 3 things that are attached to the carbon. We're not counting the other carbon. Okay, so, let's use some colors. So the H2 and the Cl, we're going to put on that carbon. Doesn't matter which place you put them in. Let's draw the staggered one first. We'll use green for the other carbons, hydrogens. So if we're going to do the staggered, then the other carbon is going to be coming out here, and it will have 3 hydrogens on it. So that's staggered. So the ones where I can see the lines all the way to the center, those are on the carbon closest to me. And the ones that are coming out from behind this circle are the ones on the carbon that's behind. Any questions about that? So then over here I'm going to draw the eclipsed conformation. So in the eclipsed conformation, these are going to be essentially on top of each other. We don't draw them right on top of each other because then we can't see what we're doing. So we draw them really, really close to each other and we understand that they're on top of each other. Now the guys in the back were the green H's, so I'll put those in there. And then in the front, we had 2 hydrogens and chlorine. So on my model here, this would be, you guys looking at this, would be the eclipsed one. And staggered, if we rotate that bond a little bit, now we have the staggered one. Does that make sense? These model kits are really useful. They can be purchased lots of different places. Amazon is probably a great place. I don't know if they have them at the bookstore. They should, but who knows. You can also substitute gumdrops or mini marshmallows and toothpicks, but you may have larger dental bills because of that.